Okay, here we're going to be talking about classification of some first order differential equations. Not all possible first order DEs fall into one of these forms, but a lot of the ones that we can actually solve do. So everything here, these will all be first order, meaning our highest derivative is a y prime, first derivative. A couple of different ways we can write a first order DE is y prime or dy dx equals, and then everything else will be over here, some function of x and y. Or we can write our DE in what we call differential form, where we have some function times dx plus some other function, possibly of x and y, times dy equals 0. So differentials are not actually algebraic quantities. We say m times dx. This is not really an algebraic quantity. We can't really multiply by it. It's an infinitesimally small object. But it turns out mathematically you can pretend they're algebraic quantities and treat them as such. And you'll see that as we go. So here we have some first order dE. To put it in standard form, I want to get the dy dx by itself. So I would move the cosine x times y over, divide everything by 2x. So now we have our derivative equals a whole bunch of x's and y's. So standard form looks like this. Our little f of xy would be all this stuff over here. To put that same guy into differential form, again, differentials, dy's and dx's, this is not really a fraction. That's not really dy divided by dx. That's the limit as delta x goes to 0 of delta y over delta x. But it turns out mathematically we can actually pretend like that is divided by dy divided by dx and treat it like that, and everything just turns out it's really nice. It works out. So we could take this equation and just multiply through by this dx to clear the denominator, so to speak. So multiply through by dx. So here the dx would cancel, pick up a dx here and a dx here. And now get our dx's together. So these two are like terms in dx. So when we move the e to the x dx over, factor out the dx, we get this equation. So we would call this differential form. It's the same differential equation. This was just the way it was written here. This was standard form. This is differential form. And then we give a name to this thing in front of the dx. We call that m. Notice it might depend on x and y. Here, in fact, it does. And this thing here in front of the dy we call n. And again, it might depend on x and y. This one only has an x in it. Okay, those will be helpful as we look at all of our different types of equations. Linear DEs in first order are obvious. You can just look at them and see whether we put them in some special form or not. We only have y to the first power, or no y at all, and we only have y prime to the first power. No e to the y's, no cosine of y, no logs of y, no y to the fifth power, nothing like that. A linear DE has only linear functions of y. It's helpful when we have a linear DE to write it in this form, where p of x is our coefficient in front of our y that may have x's in it, and then this q of x is this constant function of x. I shouldn't really call it a constant, but it's just a function of x, and it doesn't have any y's in it over on the other side. When we go to solve these, we're going to use integrating factors, and this is the best form to have it in. So this guy here is a linear DE in y. Sure, we've got some nonlinear stuff going on here, but nothing nonlinear in y. I've got a y to the first power and a y prime to the first. if I want to put this in this weird looking form here, I just got to get the y prime by itself. So divide everybody by x squared. Move this guy here to the other side. So this sine of x over x squared is what we would call p of x. And this guy here is what we'll call q of x. Again, we're not solving any of these DEs yet. Nothing here is a solution. We're just writing this in a particular kind of form, a special kind of form, so that when we go to solve it, it'll be a little easier. Bernoulli DEs are a lot like linear, but they've got this extra factor of y to the n hanging out. So this would be a Bernoulli DE. So it's got a y prime in it, it's got a y, and it's got this extra thing, y to some power in it. And so n here would be 7. Notice that all linears are Bernoulli. Like this form right here just has y to the 0 over here on the end, so all linears are also Bernoulli. Homogeneous differential equations. I don't know who came up with this name. I know why they gave it this name, but I wish they hadn't. When we get to higher order DEs, second, third order differential equations, the word homogeneous has a 100% completely different meaning from what it has here. So you want to keep that in mind. I'm going to be talking later about homogeneous second order DEs. Those are easy. Those are a lot of fun to solve. The word homogeneous means something 100% completely different. It means you've got your DE in standard form. If you were to replace all your x's and y's with tx and ty respectively, all those t's, all those extra t's would cancel out, and you would get back to the original function. Okay. What this means is if you rescale x and y by the same amount, it doesn't change your function. That's what the word homogeneous means in this context. So this guy here is a homogeneous first order differential equation. We're in standard form. Y prime is some function of x and y. If we were to go in this right hand side and replace all the x's with a t times x and all the y's with a ty, top and bottom everywhere, well, here we would get on top, we could factor out a t squared. On the bottom, we get a t squared. Hey, those t squareds cancel, and it was like the t's were never there. We get right back to the original. That is a homogeneous first order differential equation. Okay, next we have separable differential equations. These are actually the easiest to solve out of everything we do all semester. Well, maybe not the easiest. Homogeneous second order with constant coefficients are probably the easiest. These are the second easiest. So we have some DE that's in differential form. If this guy here in front of the dx is actually only just a function of x, there are no y's there, and if the guy here in front of dy is only a function of y, it has no x's. In other words, if all your x's are together here with the dx and all the y's are together here with the dy, then you have separated. You have a separable DE. So you can write your function, if you want, all the y's on the left-hand side of the equation, all the x's on the right-hand side of the equation. And then when we go to solve these, what's the next thing we're going to do? It's easy. We just integrate both sides. Okay, this is a separable differential equation. Okay, so if we write it in standard form, dy dx is x squared over y to the 7th, and we cross multiply. Again, differentials aren't really algebraic quantities. You really can't multiply dx to the other side, except that we can pretend we can, and it turns out it works. So cross multiply here, and look, all the y's are on the left side, all the x's are on the right side. That's a separable DE. Or if we write that in our standard or our regular old differential form, here's our m is x squared, only depends on x. Here's our n, negative y to the 7th, that only depends on y. That's a separable differential equation. Okay, and then finally, exact differential equations. We'll spend a day talking about these. Once this clicks for you, these are actually really easy to solve. It's just kind of a weird concept. So in differential form here, we've got this function that might depend on x and y, dx, plus another function that might depend on x and y, dy equals 0. The dE, we say it is exact if the partial of this guy, the one in front of dx, if his partial with respect to y is the same as the partial of the other guy with respect to x. We call these the mixed partials. So the guy in front of dx, I take his partial derivative with respect to y. The guy in front of dy, I take his derivative with respect to x. If we get the same thing both ways, then that dE is exact. So a little foreshadowing here. What that means is this differential equation we have here was the exact full differential of some higher dimension function. Some function of two variables, some f of xy. Remember, the differential of a function is the partial with respect to x dx plus partial with respect to y dy. So what we had here was some function. When we took his full differential, we got our dE. So that means since his full differential was 0, the only way that's possible, he must have been equal to a constant. Okay, we'll discuss that later though. We're not ready to solve those. All right, so we have this differential equation here in differential form. So the stuff in front of dx we call m. That's 2xy. Remember, when you're taking partials, treat everything else as a constant. So the partial derivative of 2xy with respect to y is just 2x. X is a constant as far as y is concerned. Okay, the other part, n, is all the stuff in front of dy, x squared plus 3y squared. I take his partial with respect to x, treating y as a constant. So for example, the derivative of 3y squared dx is 0, because y is a constant. Derivative of a constant is 0. The partial of x squared with respect to x is 2x. Hey, I got 2x both ways. That means that was, in fact, an exact differential equation. So this dE is exact.